The physics definition of a vector is it is a directed line segment. That means it is a segment of a line and it has a specific direction and length. The length is also called the magnitude, and the direction can be denoted by just pointing out what the initial and terminal points of your vector are, or it can be denoted by an angle measured from an axis. Unless told otherwise, the standard way to measure the angle is to measure it from the positive x-axis counterclockwise. But you might see diagrams in which an angle's measured from a different axis, so always look at the diagram to make sure you understand what angle is actually being referenced. The physics definition of a vector is it is a directed line segment. That means it is a segment of a line and it has a specific direction and length. The length is also called the magnitude, and the direction can be denoted by just pointing out what the initial and terminal points of your vector are, or it can be denoted by an angle measured from an axis. Unless told otherwise, the standard way to measure the angle is to measure it from the positive x-axis counterclockwise. But you might see diagrams in which an angle's measured from a different axis, so always look at the diagram to make sure you understand what angle is actually being referenced. Note that the length of the vector, again also called the magnitude, is the length of the hypotenuse of a right triangle. Because unless a vector is directly on the x or y axis, it will serve as the hypotenuse of a right triangle, in which one side of the triangle is telling you the y component of the vector and the other side of the right triangle is telling you the x component of the vector. And Pythagorean theorem comes into play to tell us the length of a vector. So our example here, we have a vector 10, 5, and its length will be the square root of 125 because the x side has length 10 and the y side has length 5. So 10 squared is 100, 5 squared is 25, then 10 squared plus 5 squared equals 125. So a squared plus b squared equals c squared. So c, being the hypotenuse, would then have length the square root of 125. Another example, if we had the vector with initial point 0, 0 and terminal point -8, -3, the length of that vector, again using Pythagorean theorem, would be the square root of 73 because the x length has length 8, so 8 squared is 64, and the y length is 3. 3 squared is 9. 64 plus 9 is 73. So a squared plus b squared equals c squared. So the length of the vector is c, which would be the square root of 73. So for all vectors, Pythagorean theorem can just be used to find its length. I just stated that you could use the Pythagorean theorem to find the length of any vector, and that is true. But if your vector is just directly horizontal or vertical, so for example, we have a vector directly on the x-axis with initial point 0, 0 and terminal point 6.50. You can see by just looking at the vector and looking at the diagram that its length is 6.5. You don't really need to use the Pythagorean theorem. But if you did, and you used a squared plus b squared equals c squared, 6.5 squared would be some value, add 0 squared, and it still equals 6.5 squared. And so if c squared equaled 6.5 squared, then c would be 6.5. So technically you could still do Pythagorean theorem, you're still going to get 6.5 as your length. But it's much quicker to just look at the diagram and see, hey, this vector has length 6.5. We have another vector with initial point 0, 0 and terminal point 0, -5. So this vector is directly on the y-axis. And we can see from just looking at the diagram and thinking about the vector that its length is 5. I'm not going to say its length is -5. I'm going to say its length is 5. Length and volume and area, they're always stated as a positive value because they are some measurement. Now, we've shown examples where the vectors have initial point 0, 0. Vectors can actually start anywhere on your grid and land anywhere on your grid, but a lot of times, even when vectors start off at another point with an initial point that's not 0, 0, to simplify matters, we often transfer the vectors so that they are situated starting at 0, 0. But in general, a vector is just a directed line segment that starts at a point. It can be 0, 0, it can be any point, and goes to some other point called the terminal point. Vectors are directed line segments. That means that they have a direction. And you can mention the direction by just stating the initial and terminal points, and to go from the initial to the terminal, it's telling you which direction to go. But also you could measure the direction with an angle. The standard is to measure from the positive x-axis counterclockwise. So unless you're told otherwise, if you are given an angle for a vector, you should assume it's measured from the positive x-axis counterclockwise. However, you might see diagrams in which you're measuring headings or bearings, and they're measured from north or the y-axis clockwise. Or you could have a diagram in which they use the most convenient angle, the one that is closest to the nearest axis. So always look at your diagram to double check what angle you're really referring to. But if there isn't a diagram and they just state an angle, assume that it is measured from the positive x-axis counterclockwise. So we have two examples here. Our first example is a vector that's just in quadrant 1, and it starts at 0, 0 and ends at 10, 5. And hence, you have a right triangle whose opposite side is 5 and adjacent side is 10. And so using inverse tangent of 5/10 gives me 26.56 degrees. So this vector has angled 26.56 degrees. The other vector is down in quadrant 3. So its opposite side has length 3 and its adjacent side has length 8. So if I take inverse tangent of 3 divided by 8, I'm not going to get the correct angle measured from the positive x-axis counterclockwise. I need to realize, hey, that's the angle to the nearest axis. So the angle between the negative x-axis and my vector. Add a half circle, add 180 degrees, and you will get the full angle needed to measure from the positive x-axis to that vector. So inverse tangent of 3 divided by 8 plus 180 degrees gives us 200.55 degrees. That is the correct angle for the vector with terminal point -8, -3. Due to our right triangle definitions of sine and cosine, there's a connection between the components of a vector and the use of sine and cosine. So look at the vector with terminal point 10, 5. The x component is the adjacent side to the angle. Cosine of theta in a right triangle is adjacent divided by hypotenuse. So if you wrote down cosine of 26.56, it would equal 10 divided by the square root of 125. Hence, solving for the x component, you can multiply both sides by the square root of 125, and the magnitude of the vector times cosine of your angle measured from the positive x-axis gives you the x component of a vector, and that will always be true. You always can find the x component by taking the magnitude and multiplying by cosine of the angle, as long as the angle is measured from the positive x-axis counterclockwise. Sine is opposite over hypotenuse. So if I took sine of 26.56, it should equal 5 divided by the square root of 125. If I solve that for the y component, I would get the square root of 125 times sine of 26.56 degrees. So again, that will always be true if you measure your angle counterclockwise from the positive x-axis. Sine of that angle times the magnitude will always give you the correct y component. So if I use 200.55 degrees for the other vector that's in our diagram, we can double check that the square root of 73 times cosine of 200.55 degrees, it equals -8. Cosine of 200 point something degrees is negative. Sine of 200.55 degrees is also negative, and so the square root of 73 times sine of 200.55 degrees gives us -3. So again, the x and y components always can be found by taking the magnitude and multiplying by cosine or sine of the angle, as long as the angle is measured from the positive x-axis counterclockwise. By the way, when you list the x and y coordinates of your terminal point, that is called the component form of the vector. That is assuming that the initial point is the origin. If your initial point is not the origin, you're going to need to just explain that in words or draw a diagram showing that your vector starts and stops at other positions besides the origin. Adding vectors is very logical whether you look at it as a diagram or just look at the components. To add vectors, you add like things, like you always do. We always add like things in math. So I add the x components, I add the y components. So for the two vectors we've been working with, -8 is one x component, 10 was the other, -8 plus 10 is 2. -3 was the y component of one vector, 5 was the other, -3 plus 5 is also 2. So those two vectors, when added, end in the vector 2, 2. We call that the resultant. So whenever you do some sort of arithmetic with vectors, the answer is called the resultant, but usually that term is used when you're adding vectors. It's also very logical to realize that if you picked one of the vectors up and did not change its direction at all, you kept the same direction and kept the same length, but moved it so that its initial point was now the terminal point of the other vector, then the vector is going to land at the answer to the sum of the vectors. So if I pick up 10, 5 and I stack it at the initial point or the terminal point for -8, -3, you can see that it lands at 2, 2. So very logically, adding vectors literally is just adding the like components. It also literally is picking up a vector and stacking it at the terminal point of another, and where that vector now lies, having moved its initial point, is the answer to adding vectors. The direction that you add never matters, so it doesn't matter if I stack 10, 5 at the terminal point of -8, -3, or if I stack the terminal point of -8, -3 at the end point of 10, 5. So here it's showing I picked up the green vector and stacked it at the terminal point of the blue vector. Notice I still land at 2, 2. So the order that you add vectors certainly doesn't matter. There are two products for vectors. One is called a cross product and one is called a dot product. We are going to study the dot product in our trigonometry class. In other math classes, you might study the cross product. The dot product gives you a scalar or a number. It does not give you a vector. The cross product does produce a vector as the answer, but the dot product gives you a number as the answer. What you do to create the dot product is you multiply like components. So A times C, they're both first components or X components, and you multiply B and D. They are both Y or second components, and you add the products. So given vector AB and vector CD, the dot product is A times C plus B times D, and again that will be a number. It's not a vector, it's a number. Not very surprising, the opposite of a vector is a vector that points 180 degrees from the other vector. So you'll hear people say they did 180, meaning they did a complete turnaround. That's what the opposite of a vector is. So -8, -3's opposite vector is 8, 3, and 8, 3's opposite vector is -8, -3, and the two of them point in 180 degree opposite directions. In algebra class, we learned that subtracting is the same as adding the opposite. Same holds true in vector land. If I subtract a vector, it is equivalent to adding the opposite of the vector. So if I wanted to subtract the vector 8, 3 from the vector 10, 5, I could add -8, -3, and that would give me the same result. So 8, 3 is the opposite of -8, -3. So if you take 10, 5, and you add -8, -3, you're going to land at 2, 2, but that's the same as subtracting the opposite 8, 3. So 8, 3 is the opposite of -8, -3. Subtracting 8, 3 gives me the same thing as adding -8, -3. This is a very nice diagram from the Time Zero blog showing the definition of true bearing, true heading, and relative bearing. The heading is the direction in which a vessel is pointing relative to north. So your vessel could be a ship or a drone or, a car. I mean, whatever vessel. Usually it's boats and planes are the vessels that we're talking about. The bearing is the angle to the target relative to north. So again, both the bearing and the heading are both measured from north. So it's like they're measuring from the y-axis, and they're measuring clockwise and not counterclockwise. So bearings and headings are both measured from north, and they're measured clockwise. The relative bearing is the angle to a target relative to a ship or plane's heading. So it's basically the angle that the ship needs to adjust in order to get to its target. Word unit attached to something in a mathematical sense means that it involves the length 1. So the unit circle is a circle whose radius is 1. A unit vector is a vector whose length is 1. Every vector has a unit vector. A vector that points in the same direction but has length 1. A slight exception to that is, and you study this more in linear algebra, but the zero vector means just the origin, the point 0, 0, 0, and it technically really doesn't have a unit vector. Or you could say every vector of length 1 is its unit vector, but we're not going to get into that in our class, okay? So a unit vector is a vector that points in the same direction as another vector, but our unit vector will have length 1 and the other vector might not. Okay, again, unit vectors, if they already have length 1, they're their own unit vector. So any other vector that does not have length 1, its unit vector is a vector that points in the same direction but has length 1. So how do you find a unit vector? Well, if you take any vector and you divide each component by the length of the vector, you will create a vector that has length 1 and is still pointing in the same direction. So let's just point out, first of all, if you take a vector and you multiply the vector by some real number, you're going to get another vector that still points in the same direction. Multiplying a vector by a scalar does not change the direction unless you multiply by a negative scalar, and the direction will be exactly 180 degrees in the opposite direction. So if you multiply by a positive scalar, you're going to change the length of the vector, but not the direction. So if I specifically multiply by 1 over the length of the vector, I will get a vector that points in the same direction, but has length 1. So our example here for -7, 3 is pointing in a certain direction. If you take 4 squared plus -7 squared plus 3 squared, you get 74. So the length of this vector is the square root of 74. So if I multiply each of those components by 1 over the square root of 74, I will get a vector that points in the same direction but has length 1. So you can see in our diagram here, I have the vector for -7, 3. It has length square root of 74, but then little tiny but pointing in the same direction is its unit vector, and the numbers are kind of messy for the unit vector, but the concept is fairly straightforward. Divide each component by the length of your vector, and you will create a vector that points in the same direction but has length 1. You can always find the angle between two vectors by realizing that cosine of the angle between them is equal to the dot product, not of the vectors, but of the unit vectors. So given two vectors, first find their unit vectors. Once you have their unit vectors, if you find the dot product of those unit vectors, you will get a real number that is equal to cosine of the angle in between. And then you can use inverse cosine to actually find what that angle is. So for our example here, we have 4, -7, 3. We already talked about how the length of that vector is the square root of 74, because 16 plus 49 plus 9 equals 74. We have a second vector, -2, 2, 6. And if I take 2 squared plus 2 squared plus 6 squared, I get 4 plus 4 plus 36, which is 44. So the unit vector for 4, -7, 3 is 4, -7, and 3, all divided by the square root of 74. And the unit vector for -2, 2, 6 is -2, 2, 6, all divided by the square root of 44. So multiply the x components. So 4 over square root of 74 times -2 over square root of 44. Multiply the y components. So -7 over square root of 74 times 2 over square root of 44. Multiply the z components, or the third component. So 3 divided by the square root of 74 times 6 divided by the square root of 44. And then you add those products, and in this case we get -4 divided by the square root of 3,256, because 74 times 44 equals the square root of 3,256. So cosine of the angle we're looking for is equal to that number. So plug that number into inverse cosine, and I get 94 degrees. So the angle between these two vectors is 94 degrees. Cosine of 94 degrees is equal to the dot product of their unit vectors. To wrap up our introduction of vectors, there are a couple of other important things to recognize. We just got done talking about how to find the angle between two vectors. Cosine of the angle between two vectors is the dot product of their unit vectors. Well, what if that angle is exactly 90 degrees? What is cosine of 90 degrees? It's 0. So if the dot product between two vectors is 0, you know they're perpendicular. So that's often a test to see whether or not two vectors are perpendicular. By the way, the word perpendicular can also be referred to as orthogonal or normal. So you might hear orthogonal and normal, and those words mean perpendicular. So vectors are perpendicular or if their dot product is 0. And that's because cosine of 90 degrees is 0. Also, if you're working in 2 dimensions or 3 dimensions, there's some shorthand notation that's commonly used. The vector that points directly down the x-axis is often called I. So if you're in 3 dimensions, x is 1, y and z are 0, so the vector is 1, 0, 0. That's the terminal point of the vector. If you're in 2 dimensions, you don't have z, so x is 1 and y is 0. And that's, again, it's the vector that's going to point directly down the x-axis, but has length 1. So it's a unit vector. J is commonly used for the vector that points in the y direction. So if you are in 3 dimensions, the vector with terminal point 0, 1, 0 is J. If you're in 2 dimensions, then x is 0, y is 1, there is no z. If you are in 3 dimensions, the vector that points directly in the z direction with length 1 is often referred to as k, and x and y will both be 0 and z will be 1. So these are common unit vectors that kind of represent our 2D or 3D space, and I, J, K are letters that you should sort of become familiar with being used as references for these vectors. We also need to cover the definitions of component and projection, but there is another video that goes over those definitions. In general, though, the component of a vector is the length that a vector casts onto another vector. So picture 2 vectors, and one, if there was a light source right above it, would project a shadow onto the other vector. The length of that shadow is the component, and if you turn that segment, that is the shadow, into a vector itself, the shadow segment turned into a vector is called the projection. So the component and projection are almost the same thing. The component is really just talking about the length, the magnitude, and the projection is that length turned into a vector itself. I mentioned that a component is a length, but components can be negative, and if a component is negative, it means that the vector that is sort of serving as the shadow is pointing in the opposite direction of the other vector. So if vectors are pointing in such a way that the shadow points in the opposite direction of the second vector, its component will be negative. Our basic discussion about vectors.